Perfect. Okay, let's get started. Hello, everyone. Good morning, or good afternoon, or good evening, perspective to where are you? Thank you for joining us today for this webinar organized by the Canadian Geotechnical Society Young Professional Committee. My name is Rajit Dayaratna. I am a geotechnical engineer from St. John's, Newfoundland, and I am serving the CGS YP committee as the knowledge lead. We initiated this webinar series to allow young professionals to enhance their knowledge in a range of areas of geotechnical engineering. Our last webinar was held in January, and Dr. Lucas Aronson from BGC Engineering delivered an introductory lecture about permafrost engineering. If you are interested in listening to his talk, the recording is available on our YouTube channel, and I posted the link in the chat. Before we get started, there are few housekeeping notes. To avoid any disturbance, audio and video access has been disabled. If you have any questions, you can use the chat option. Presentation will take only about 40 to 45 minutes, and there will be a brief Q&A session at the end. If you have any questions for speakers, please type them in the chat, and I will take them as they appear. Before I introduce today's speakers, I would like to hand over the floor to our chair, Dr. Sharma Roy, to share a few words with you. Over to you, Sharma.
Thanks, Rajit, and hi, everyone. As Rajit mentioned, my name is Sharma Roy. I know it's pretty hard to pronounce my first name because it starts with K, but K is silent, so you can call me Sharma. And I'm the inaugural and founding chair of the Canadian Geotechnical Society Young Professional Committee. So before we jump into the details, let's start with a safety moment. And my today's safety moment is walking regularly. So if you walk at least a few times a week for about 30 minutes or longer, you can greatly improve your cardiorespiratory fitness and function. And becoming a regular walker leads to stronger bones, better range of motion and flexibility, improved capability to control body weight, and improved mental health. And something that is really close to my personal experience as well, walkers tend to be good sleepers. So I had issues with sleeping well, but the walking regularly helped me a lot. So if you want to know more details, there's a link on the bottom of the screen, so you can have a look. So now the Young Professional Committee is a brand new committee established in late last year with a focus to bring together all the young professionals of our community in an organized forum. And by young professionals, we mean those like many of us who have less than 10 years of experience. And our vision is simple, building the next generation of geotechnical leaders. Based on the vision, our mission is supported by 5 pillars: network, knowledge, development, collaboration, and impact. The committee will provide a network for our peers and veterans, create avenues for building geotechnical knowledge, provide access to both personal and professional development, create opportunities through collaboration with industry, academia, government, and other young professional groups outside CGS, and create an impact by articulating a vision for the future within the changing industry landscape. As you can see, we have a diverse leadership team representing young professionals from industry, academia, including both professors and students. 77% are actually from industry and 23% from university, both men and women, with 55% of women. And almost all provinces in Canada, right now we have representatives from 8 out of the 10 provinces. So we have created a LinkedIn group for the young professionals, and we already have over 170 members. So I strongly encourage you to join the group if you haven't done so. And besides this, please check out our new website section under the main CGS website. And don't forget to subscribe to our brand new YouTube channel. We have taken some major initiatives within a few months of being formed. This year, we have started a pilot CGS mentorship program and also this webinar series. A few other exciting initiatives are also on the planning. For example, National GeoL competition, non-technical webinar series, K-12 school outreach, and in-person social events. If you're an enthusiastic and active young geotechnical professional who's interested to be a part of any of these great initiatives, please reach out to me or any other leadership team members. We have a few subcommittees where we can help us in executing some of these initiatives. With that, thanks again. everyone for joining in today, and I will pass it to Rajiv to introduce our speakers today.
Thanks, Shama. I'm pleased to announce that we have two experts today from Isherwood Geostructural Engineers. Isherwood specializes in underground geostructures and client delight. And it is a boutique company committed to a superior quality and service, and is an acknowledged leader in its niche field of urban excavation, shoring, and specialty foundation design. Our first speaker, Carol Domitric. I'm very sorry if I mispronounce your name, Carol. She's a partner and principal engineer at Isherwood, where she has 25 years of geostructural design and field experience. Carol studied civil engineering at Queen's University. Her work at Isherwood includes Toronto Transit Commission transit projects, most recently the new Eglinton Young Station, and many GTA and Vancouver deep excavation, and particular experience with tied back shortcrete shoring. Carol currently oversees numerous engineering projects, leads safety and education programming, and has been a significant contributor to the in-house development of resources and tools, and is currently working on a major education initiative to develop an online accessible fundamental education system for Isherwood. Our second speaker, Erika Acton. Erika joined Sherwood in 2011, first as a student intern and then as a full-time engineer in 2013. And she has been instrumental in implementing Sherwood's quality management protocols and has been a team leader since 2019. Erika is a licensed professional engineer in Ontario and British Columbia, specializing in temporary shoring and specialty foundation design, with a focus on subway projects and high-rise condos. Some notable projects Erika has contributed to are TTC Young University Line Expansion, Eglinton LRT's Young Eglinton Station and Laird Station, and Waterfront Toronto East Bayfront Development Dock Wall Replacement. So you see, we have two well-experienced engineers, especially in soil retaining structures. So without further ado, I would like to invite Carol to start their talk on soil retaining structure. Over to you, Carol.
Thank you very much for that wonderful introduction. It's really great to hear this initiative you have with the young professionals. So I am happy to contribute to that today. Okay, so Erika, you're going to bring up our presentation for us, I believe. Yes, there we go. Thank you. So we're going to talk about some basics of soil retaining structures today. So soil retaining structures 101. Next slide, please. So we've already been introduced, and I do want to say a word that Erika joined me some years ago when I was working on the Vaughan Corporate Center subway station, and it was remarkable to see her growth as an engineer, taking on those projects to recent years where she was the lead engineer on our young subway station. So I'm really happy to be working with her on this presentation today. Can I have the next slide, Erika? This is to give you an idea of what we bring, what experience we bring with us, just to show you. Isherwood is founded from our office in Mississauga, and also today has an office in Vancouver, and we've done projects throughout North America. We are focused, a lot of our projects are focused in the GTA, as you can see here. And we have quite an archive of previous experience that we draw on. So, when we learn about engineering at school, this is something that's talked about, and I really learned that in action when I came to Isherwood and saw how much more it brings to your perspective when you start to actually draw upon real world experience, monitoring data, and the experience of other more senior engineers who help to bring you along. I pulled out of our archives this sample of a project that was done by our founder, Brian Isherwood, back in 1974, when he worked on a portion of the shoring for the CN Tower. The CN Tower, of course, is familiar to all of us, so that adds some interest. You can also see, the progress of a design here, the great care Brian would have taken on the left-hand side there, putting together his lateral pressure diagram and his calculations. And then at the top of the page, you can see the thought process, like working through the sequence. We can design theoretically, but how the system is actually installed, the sequence that it's installed in, and all the particulars of the site conditions, who the contractor is you're working with, what type of equipment they're using. These are all things that factor into the design. And Brian was very knowledgeable, an experienced engineer in that regard, and worked closely with contractors. And you can see the care he would take to think through the process of the work. And then in the middle there, you can see sort of the final product of detailed notes and details of how the pile and the caisson were going to be constructed. So I think this just gives us a good sort of idea of some larger concepts that we're going to touch on as we go through the rest of the presentation today.
So I wanted to just give a little bit of context of the different types of earth retention systems. The Canadian Foundation Engineering Manual, they have one chapter for rigid earth retention systems, which are the gravity wall and bridge abutment wall example on the left-hand side. And they have another chapter focused on flexible earth retention systems, which are cantilever and tieback wall examples on the right-hand side here. The difference is, in simple terms, is that the rigid systems kind of move all in one versus the flexible systems kind of deform as soil pressure and water pressures are added to them. Isherwood, we specialize in typically in temporary earth retention structures, which tend to be flexible systems. So that's going to be the focus of today's presentation. There's definitely lots that carries between the two systems, but we want to make sure we kind of keep our focus a bit narrow so that we can give you some good things to pull away and some good understanding on the one side, but you can definitely pull a lot of this for both types of retaining systems. So to start with, we'll just talk about why we really are doing this. Why do we need soil retaining structures? So this is just a little video. I don't know if you're going to get the sound or not on your end, but so this is just, I'm not sure if the sound went through, but he explained that
No sound, Erika. That's fine. Yeah.
there was no sound? Or
No, there was no
Okay.
sound, Erika.
So they said that if a 6-foot deep trench collapses, that could be 10 tons of soil. So even for something that many of us might think is a fairly shallow excavation, like 6 foot deep, it's about the height of I guess a tall person. It can put 10 tons of lateral pressure on you. So that's why even for smaller excavations, retaining the sides of them is very important. And then we have another video from one of our sites out in Vancouver, close to the coast. And water pressure is another big driver. I'm guessing you can't hear the sound here either, but yeah, you can see this is a tieback anchor, a soil anchor being drilled through a shoring wall, through a retaining wall, and you can see a lot of water pressure coming through. And you can see it's very muddy water. It's bringing soil with it. And that's kind of, you can just see how much pressure you're holding back with the retaining wall systems. So I mentioned soil conditions and groundwater are two of the things that we're considering when we're designing a retaining wall system. You also should be thinking about what's at risk, which I have a slide next to show that, and also the geometry, like where are the utilities, where are the neighboring structures, how deep of an excavation do you need to build, or how deep of a opening do you need. So this slide kind of demonstrates, it goes through what's really at risk. So that's something that's very important to consider. If you need an excavation in the middle of the country where there's nothing sensitive nearby, no sensitive utilities or sensitive buildings, then you can let things move a lot more. This middle one is kind of an intermediate condition. It was a cofferdam on the side of a river where quite a bit of movement was acceptable. We just needed, it was on the side of the river, so you needed something to hold back the water, but we weren't protecting anything too sensitive. Versus on the high risk end, we have this job site in downtown Toronto where you can see there's like a high-rise building. I'm not sure if you can see my mouse, but a high-rise building to the right, and then some sensitive buildings just kind of straddling the corner of the site, and some, this is, you can't see it actually, but there is a subway, underground subway box running directly beside it as well. So you definitely need to consider the risk when you're designing the retaining wall systems.
So I'll jump in here just to give an overview of the typical elements of a temporary supportive excavation design, starting with the inputs. And I can't stress the importance of this enough. So just determining what parameters one's going to use, and a whole lot of information that we have to be aware of in order to start the design. And we'll touch on this in some future slides. Step 2 will determine our lateral pressures. And here there's some judgment in terms of distribution that we would use. Again, I'll touch on that a little bit later. Then knowing the industry and what type of equipment and materials contractors are likely to use will make some judgment about what pile size to try to use to select. Consider what level, how many rows of supports we're going to require and where to place those. We'll develop a simple model to make some determination of things like pile moments that we'll use to design the pile for strength. Then we'll consider capacity of supports that we would need. Again, revisiting that topic of how are we going to distribute the loads? Where can we develop capacity? Depending on different factors like perhaps soil conditions and which layers are stronger and better to develop an anchorage in. Once we've determined, say we're using preloaded tiebacks, we now will have introduced some vertical loads into the system, and we now have to revisit the pile size and consider the axial forces combined with the bending moment. So we would do that refinement. Now we're going to check our toe and ensure that we have sufficient penetration to get the reaction force that we require at the base of the system. And then finally, we'll summarize our design that we're going to then take forward and incorporate into the drawings that are going to express the design and be used on site to build the system. So today we're going to focus in the 5 circled areas, as we won't really have time to get into the details of everything.
Okay, before we get into some kind of design steps of how to approach a problem, we're just going to go through some examples of the type of systems that we tend to design, so you can get a feel for the wide range that you might be looking at, the different applications and that sort of thing. So this is a soldier pile and lagging wall, which is drilled piles or driven piles with timber lagging in between the bays to support the soil. And in this case, it's supported by tieback anchors, which you can see the heads of the tieback anchors on the wall, and they're extending into the soil behind the wall. This is a caisson wall system or secant wall system. Internationally, it's referred to as secant wall, and in the GTA, we tend to call it a caisson wall. It's interlocking drilled pile holes filled with fairly weak concrete, normally between 2 MPa and 6 MPa. And again, we have piles, steel piles, and supported by tieback anchors that you can see the heads of the anchors sticking out of the wall. And here's another example, which is another soldier pile and legging example, except it's 8 levels of underground. And once we hit, this is the Shangri-La Hotel, I believe, in downtown Toronto. Once we hit the bedrock in Toronto, we just exposed the bedrock instead of legging all the way down because the rock is fairly self-supporting. Another example, this is a secant wall shoring project that's up against Lake Ontario. So it's supporting both water pressure and soil pressure, and needed to be used to help create an excavation in the dry so that they can actually build the condo building that they were putting in here. Shoring is also frequently used to support, at least in Toronto, where there's historical buildings that they need to keep the facades of for their building. We use it to support the facade system on as well. So this is an example. You can see soldier pile leggings shoring below one, and then a caisson wall shoring below the other example on the right. And then the historical facade is held up in the air, sitting on the piles. And another example with soldier pile and legging and secant wall shoring next to active train tracks. And this last example, I believe this is the last one, is an excavation support system, and it's also supporting a historical building on a slab, but excavating below it because the developer needed to put some parking in. And utilities normally come into play when you're working underground. So in this example, you can see lots of utilities hanging from a decking system. There's a steel deck system that allows the traffic to keep driving. This is, I believe, at Keele Station on Eglinton Avenue. And then you can see the shoring off to the left here as well that the deck is sitting on. And here's one more complex, here's one more complex example that has a lot of struts supporting a shoring system next to a neighboring building. And Carol, back to you.
Thanks, Erika. Here you can see, so at Isherwood, we use a database system to keep our archive of project data. And here we're showing the active job that we're working on is in green, and we have some neighboring jobs where we've already done work. So drawing on our experience and our knowledge of the local geology is very important. So this sort of just gives you a little cartoon of the process that we go through. At each of those sites, we keep the geotechnical reports so that we have access to information about the soil types. We also, having done tieback testing on those sites and having done monitoring on those sites, draw on all of that information to inform our design in that local area. Here's an example of a project where we have received just a geotech report with just 2 boreholes, which isn't enough data. And so it's important as an advocate for our profession to speak up to our clients and educate them about the importance of geotechnical data and let them know, what we would recommend and advise that they provide in order for us to create a more economical design, which not only will save the client money in the construction of the work, but also can help our designs to be more sustainable, which we're now acutely aware is more important than ever. In the next example, you'll see a project with a much better, much better collection of geotechnical data that we can use to inform our design. It's important to keep in mind that the soil is a very key part of the system that we're designing. The steel and the timber and the concrete are all very important, and we design that, but we're also working with the soil. So understanding what we're working with is really important. All of you will have a good base of knowledge from your academic training. And then as you apply this to your work, considering, how it influences your work is the next stage of development of your design ability. Here we want to give you an idea of the importance of developing a feel for what you're working with here. So if you just imagine a cubic meter of soil, which is about the length of your arm in 3 directions, a big cube that size, that's 20 kilonewtons of weight. I don't know if we have much interactivity in this interface that we're using, but if anybody wants to chime in as to another material that is similar in weight to soil, I'll just pause a millisecond here and see if anybody wants to contribute.
I think they are not allowed to.
Oh, they're not able to. They're not able to.
Yeah, people can't turn their speakers on.
Carol, it's only the chat option available for them. Yeah.
No worries. Okay, I'll pretend to be answering my own question. Oh, look at that. We have one answer. Thanks, Chris. Concrete, yes. Concrete is 24 kilonewtons per cubic meter. So we all know concrete is very heavy, but I don't know that people always realize how heavy soil is, even those of us who are like academically trained. So that video that Erika showed us before about the soil collapsing, that is really a key thing to be aware of as designers, the responsibility that we have for the safety and performance of our systems. And here we cover some basics that many of you will already be familiar with. The typical range of unit weight for different types of soil, and how that contributes to an increase as the deeper you go, the soil pressure increases. I'll advance the slide there, Erika. So 60 kPa when you're at 3 meters depth, 200 kPa at 10 meters depth, depending on your soil type. And then that is translated into horizontal soil pressure. So you may find it remarkable to see pictures with little children's hands in, but again, like relating back to something that we can all have a tangible understanding of. So, plasticines and Play-Dohs can be helpful in terms of understanding clays and then remembering, our experiences playing with sand on the beach and that kind of thing. So we can, from the active earth pressure coefficient, make a determination of how much horizontal pressure is exerted in response to the vertical gravity forces on the soil. And here we show Ka, which is the active earth pressure coefficient, but sometimes we're talking about an at-rest coefficient. In the table you see next to buildings and structures, we're using a higher K value because we're trying to maintain a stress state that's closer to the at-rest state. It will never be exactly the same. There's always going to be some change as we excavate, but we're trying to maintain that. And then K may vary somewhere in between active and at rest, depending on the design objectives. So now we move to lateral pressure diagrams. On the left, the Rankine approach gives us a good determination of total load. And you can see the arrows that are drawn inside the triangle shows us that triangle represents that variation in the lateral load as you increase with depth. However, as I mentioned earlier, the way the load is distributed may actually vary in reality. Rankine shows us what the stress state would look like in the unexcavated soil, but as we excavate, the total load will remain the same, but the way it's distributed may change. And an apparent earth pressure diagram approach, as shown on the right, can give us some insight into that. So these diagrams were developed based on empirical data, and they are actually envelopes that were drawn around actual data points that were gathered on sites based on strain gauge data from struts. And the envelopes were drawn so that a designer could take the apparent earth pressure diagram, the tributary contribution for that particular support, and have a force that within which that strut load would fall. And so it's a very safe approach that's based on actual real world experience. And it also shows us how here, based on the different soil types, how the distribution can vary. So this rectangular pressure distribution is actually more reflective of what we often see on sites, particularly if we're preloading the upper supports, that we'll see more load distributed towards the top of the excavation and not such an increase in pressure towards the base. And that's something we can control through preloading and experience. So here is a simple calculation of lateral pressure at the base of a 5-meter cut. And then in green, we're showing the total load per meter of excavation. And here's how that is calculated. We'll go to the next slide for a 10-meter excavation. You'll see, so now we've doubled the height of the excavation, and you'll note that the pressure at the base is also doubled. However, the total load is now 4 times what the load was for the 5-meter cut. So this is an important concept to keep in mind, similar to that other diagram where I was talking about the forces of the excavation. This concept is important, that when we increase the height of the excavation, the increase in the load is actually exponential. And then if we double the height of the excavation again, you'll see now it's 16 times what it was for a 5-meter cut. So this is simple. The math is simple, but the understanding that concept is very important. Okay, so the design life cycle is when I'm talking about those basic elements of a shoring design, we want to think about where we start. And I talked about design inputs being really important. And so here you'll see on this sketch, we haven't actually designed any shoring yet, but we've gathered a lot of information. On the right-hand side, we've got the boreholes drawn to scale so we can see where the soil layers are and where the water is. And on the left-hand side, we're showing where the existing grade is, the utilities, and the rock level, what the proposed building is going to look like. So there's a lot of information that we need to gather before we can actually do a calculation. Now here you see where the design has been actually worked out. And in this case, we're anchoring into the rock. So above the rock, we don't have very high end values. So here it's more effective to use the rock in order to anchor. Erika, I think you were going to speak to the monitoring here.
Yes. So you can see here from this example, this is a simple beam analysis, like a elastic beam analysis model. That's just modeling triangular earth pressure, which is, as Carol was talking about, is one method of modeling the soil pressure. And in this example, we calculate the moment, and you can see we have some sort of deflection output here. And we have the deflection drawn on here, just kind of superimposed to scale so that you can see how much movement we're expecting. And this little part in the middle is just a reminder to keep a sense of the scale. So you can see the predictions here are 5 millimeters, essentially 5 or 6 millimeters of movement, which is half of a centimeter of movement. So we draw this very exaggerated view just for us, for design purposes to get a feel for where the maximum movement will be, but this scale is grossly exaggerated just to keep in mind where we'll see that movement. It's actually very little movement that we're expecting. And this is the same project, and it's the actual movement that we saw on the site. And this is an inclinometer plot, so this is a monitoring instrument that's used to calculate the amount of lateral deformation. So you can see here, this is how much movement we actually saw. And you can see here, it's also grossly exaggerated. It's about 7 millimeters of movement. And I guess from the minimum of about -3 to the maximum of +7, it's about 10 millimeters, so 1 centimeter of movement. So it's controlled very closely. If you can picture 1 centimeter in something in real life, it's not something you would be able to see with your eye. Like maybe you might be able to see little cracks behind the wall, but it's not anything that you would be able to look at that wall and notice that it's actually moving. And this is just for interest's sake, a comparison to the calculated deflection. And I guess a reminder that this calculated deflection was just based on a very simple elastic beam analysis model. So it's not a very sophisticated model. It's just applying some load as if soil behaves as like as if the soil behaves perfectly triangularly. This is how much deflection you would calculate. Anything you want to add to that, Carol?
Just again to emphasize that these movements are really exaggerated, and I'd also point out that in the model you see, like the way in which you can see how unsophisticated these models can be is that if you look at the blue and you see how that is deflecting into the soil, like back into the soil at the top of the pile, in reality there's resistance there from the soil itself, and that's not, the model doesn't account for that. So that having that looking at real monitoring and having that real world experience of like what the deflected shape will actually look like helps to inform your design. And that's an important thing to pay attention to whenever you can, to try to get that feedback. Like when you do your calculation, that doesn't give you the whole answer. You still need to look for the data from the world around you.
This is another slide that just shows, again, this is just following typical, just really basic elastic beam analysis principles, where we apply the same load to both of these models, but we model the support reactions in different ways. So in this first model, we modeled the pile toe, where the pile is embedded into the soil, just as a pin support. So we're saying the toe won't move at all. And we're modeling the tieback support also as a pin support. If you want to stick with the simple model but get a little bit more complex, you can calculate the elastic rigidity of the soil anchor, of the steel in it, think about how much it will deform, and you can come up with springs that represent the soil parameters as well and model the toe as springs. You can see here in the two different models, again, very simple elastic analysis models, you're seeing two very different deflection predictions. And the bending moment predictions are not that far off, I guess about maybe 10% off for the maximum, but the deflections are quite different, the predictions.
Yeah, and that's predominantly, we use these types of calculations predominantly for determination of the moment so that we can size the pile, and we rely less on it as a deflection prediction. This is a particularly good tool for that.
So the first thing you kind of need to think about before you start the design is what questions are not yet answered, like what information don't you know? So we have some question marks here just as kind of a clue. I know this isn't a super interactive thing, so I'll just give away the answers. But if you want to think about where we're kind of missing information, then you can do that. So for example, this neighboring building, we're just assuming an underside of footing here. We don't really know what this neighboring building looks like. Maybe it has no basement, maybe it does have a basement, maybe it's a condo building and it has 5 underground parking levels and we'll be way down here and we'll need to avoid hitting it with any tiebacks. You can see we have a question mark by this borehole. You might notice that it's not very deep and not giving you the full soil profile all the way down to your base. Utility details unknown, so we don't have utility information in here right now. We need to find out that. And this is from a tutorial that we did in our office a while ago, but these were kind of questions that came up based on a similar 10-minute design brainstorming job. So we aren't going to read through all of this. I'm guessing you can't really read this based on the scale, but there's lots of questions that you need to think about before you even jump into the design. So the group in this tutorial came up with over 150 questions that really needed to be answered. And so we're going to go through some examples of how a shoring design can change based on a variety of factors. Carol, did you want to go through that, or?
Certainly. Yeah, you can jump in whenever you like, Erika.
Okay.
So here we have an 11-meter excavation with an existing building at some distance, which would typically be considered outside the influence. But as you see here, we have a short borehole with no blow counts on it. So if we were just going to assume we were in fairly competent material, this is what our design might look like. 2 rows of tiebacks and a 3-meter pile toe. However, upon getting further information, this is the borehole 09 there. That's actually what we learned the soil conditions were, and it says WH there, which is not something I'd actually encountered in my career previously, which is weight of hammer. So they're dropping the hammer and it's just falling through without needing to be tapped. So that's really soft material there. And then you can see it improves to with an N value of 11 further down. So our design changed dramatically based on this information. You can see the toe got a lot longer. The fillers, the caisson wall was extended to 6.5 meters below base of excavation. And our tieback design was revised so that the tiebacks are all anchored above the base of the excavation, because that's about the line where the soil strength drops off quite remarkably. So again, these real world factors can really impact your design. So now here's another example. We've got a proposed building. That's what the dashed lines indicate. And we've got our borehole data. Here we have competent material throughout and below base of the excavation. We have excellent material. And, again, we might say, with this distribution, we will have 2 tieback supports and our pile toe as shown. And then we're going to add more information. Well, if we hadn't gone to the site and done an investigation and checked the survey, we might not realize that there's actually an underground parking garage next door. So now how does that impact? Now we can't put the tieback, the upper tieback where we planned, and our design might look a little more like this. What if the neighboring building was actually sitting on caissons and was found out at a greater depth? In this case, borehole 102 would not apply, because it's unlikely that this building would be founded on caissons in such good soil. But say the soil was weaker and we had caissons, again, how's this going to impact our design now? Now we don't have room to put longer tiebacks. Now it's going to look something like this, and our toe design would also change considerably. So here we're showing how the proposed structure, the internal footings can affect our design. Now, if they're planning to put a deeper internal footing close to the shoring, it's going to impact our toe design. They're going to be disturbing, like excavating in front of our pile toe, so we're going to have to drop our pile toe. So again, another factor that affects our design. So you see there, the toe's been dropped. We've got some tiebacks that are diving under the adjacent existing building, and we can only put in a short deflection control anchor at the top. And now what if on this same project we got that stinky borehole with the weight of hammer soft material? Now what? So that changes our design considerably.
Okay, so the last part of this presentation is going through an interactive example. So this is where you can kind of think about how you would approach something. We only have, I'll go through it fairly quickly since we don't have a lot of time left, but that way we'll leave some room for questions at the end. But basically, we're looking at actually, I'm just going to flip through this and show you the drawing to start with, instead of walking through the example. But basically, we're looking at a developer contacted us and says that they want to install 2 underground levels of parking. So I've sketched this out really roughly. The first step is to draw the section showing the proposed excavation using an appropriate scale. And that's what we've done here in purple. We know where the ground level is. In this example section, we have a laneway and 2 property lines, and then there's another property here. So you can probably think of quite a few question marks already at this point, like who owns this laneway? Who owns this property? Are we allowed to put shoring systems on it? This looks like a pretty rough sketch. Is this really the right depth? But as a starting point, we can put a tieback at an angle of 25 degrees and sketch in lines to represent the pile and tieback. So we might put in a tieback here going in at roughly 25 degrees. And we go and look at the geotechnical information and we realize there's also some rock down here that we'll be hitting. And we look at some utility drawings and we learn there's some utilities in this laneway as well. So we've sketched this up a little bit cleaner. We've pulled the geotechnical information, and we can see that we have end values on the side of it, and we're hitting, this symbol here is for shale bedrock. So we're hitting some rock basically right at the base of excavation. And based on that, we decide to switch from a 25-degree tieback to a 45-degree tieback so that we can anchor in this rock instead of the soil above the base that isn't the greatest. So we've drawn our pile in here and then a tieback schematically. The next step is to look through the soils report and find some good design parameters that you can use. So there's earth pressure coefficients, the phi value, basically following the formulas that Carol went through earlier that were earlier in the presentation. Looking at whether there's any groundwater, like water pressure that we have to retain. What surcharge, there's a laneway, so there's probably going to be some traffic driving through there, and we should design for neighboring traffic like construction vehicles or just cars driving back and forth. And we should think about the maximum bond stress for the tieback anchor as well. So in this case, we would, if we're going to do a rock anchor, we would draw the zone of influence. So I've drawn this here. This is the active wedge of the soil is based on an angle of 45 minus phi over 2, this angle here. And we want to make sure that we keep our anchor outside of that zone. We would look at the soil and rock information, and in this case, we decide it makes more sense to elongate the tieback and anchor it in rock because we aren't quite sure of the capacity of this soil. So we're well outside of the active zone, and we're going to just anchor into the bedrock. And the next step would be calculating the earth pressure, assuming the piles are spaced at 3 meters apart. The pile spacing is something that sometimes it's an iterative process of looking at the different options. You might calculate it at 3 meters and realize that the tieback loads are too high and won't necessarily work for a typical bar design or tieback strands that you have available. And you might go back and reduce it to 2.4 meter spacing. There's a lot of things that go into that, but in this sample case, we chose 3 meters. And you can superimpose, in this case, I've just shown the soil pressure, the active soil pressure here, and then the passive resistance here. This is a really simple approximation. We do have rock down here, so rock, the passive resistance of rock, it doesn't really behave like soil. So this is just a kind of simplification, but just to kind of show you how you consider the resisting loads and the driving loads of the system. And you would calculate the horizontal reaction force at the tieback level. You can do this by hand simply, especially for a one-row design like this, where there's just the one row of tiebacks, or you can put it into an elastic analysis program and calculate it. So you can see in this case, there's kind of a little 3D sketch that Carol did to show where the piles would be and lagging between them. And once you know the load in the tieback, you would calculate the length of the anchor based on the adhesion that you can get in the rock and the load that's in the tieback. So these are some just examples showing how you could simply calculate some things by hand. So for a single support level system, just a simple way of calculating the bending moment is to calculate the average of the pressure along your worst case span. I don't know if I drew this average very well. And then use the formula WL squared over 8. And for continuous supports, when you have multiple supports, you have some continuity of the beam, so you can reduce the bending moment a little bit and use WL squared over 10. These are simplifications that can give you a ballpark starting point for your calculations. Oh no, oops. Okay. And we just have, to wrap things up, we just have a couple examples of, here's a hand sketch showing some pressure distributions just to give you guys a sense of what it might look like. So in this example, we have soil pressure going down to underside we have filler piles of a secant wall going down well below the base of excavation. We have a bunch of water here. You can see this little water symbol, and you have the water pressure going down. And then we have a surcharge pressure, and you can see the passive resistance on the other side. And this is another example where we have, you can just kind of see all of the pressures laid out just to give you an example of what a more complicated pressure distribution would look like. So in this one, we use 2 different K values, one for above the influence of the neighboring building, and then we increase the K value to better control deflection once the neighboring building starts putting load onto our system. And that's it. We have a bunch of different design references. If anyone wants, I'll go back to that. If anyone wants to take a screenshot, or you can email us and we can send it to you. But this was a really quick overview of things. So if you'd like to hear more or learn more, these are just some recommendations for a starting spot. And yeah, Carol, do you want to add anything else? I think we have 5 minutes left, so.
Oh yeah, well, I won't say too much except that, that's it in a nutshell. I hope that you were able to grasp that in the short period. That's a lot condensed into a short period. So, thanks, Erika. I think that was like those design examples provide a lot for people